Uh,
Madam.
So hello students, now we'll start a new unit number 4, canal design and canal headworks. So the first topic is introduction to canal design, canal section and bed slope and losses of water in canals. So first, introduction. So the entire water conveyance system for irrigation comprising of the main canal, branch canals, major and minor distributaries, field channels and water courses have to be properly designed. So the design process comprises of finding out the longitudinal slope of the channels and fixing the cross sections. The channels themselves may be made up of different construction materials. For example, the main and branch canals may be lined and the smaller ones unlined. Even for the unlined canals, there could be some passing through soils which are erodible due to high water velocity, while some others may pass through stiff soils or rocks which may be relatively less prone to erosion. Further, the bank slopes of canals will be different for canals passing through loose or stiff soils or rock. Next, canal section and bed slope. So canal section is designed for the discharge as worked out in column cumulative discharge of cutoff statement. Same section may be adopted for a group of adjacent outlets if variation in discharge is nominal. Bed width versus depth ratio as given below should be followed for economical section design. So, B by D ratio for different discharge is given below. That is, bed by depth ratio for different discharge is shown below. So bed width versus FSD ratio for different discharge are shown below. Discharge in Qmax, B by D ratio, discharge in Qmax, and again B by D ratio. So this table is important. Next, introduction to canal design. So the success of the irrigation system depends on the design of the network of canals. So the canals may be excavated through the different types of soil such as alluvial soil, non-alluvial soil, etc. Based on the water requirements of the crops on the area to be irrigated, the entire system of main canal, secondary canal, tertiary canal and field distributaries or main canal, branch canal, distributaries and water courses should be designed properly for a certain realistic value of peak discharge that must pass through them, so as to provide sufficient irrigation to the commons. Again, the design of unlined and lined canals involves different practical and economical consideration. The design of a channel involves the selection of channel alignment, shape, size, and bottom slope, and whether the channel should be lined to reduce seepage and or to prevent the erosion of channel sides and bottom. The design of the capacity of an irrigation channel consists of the determination of the cross-sectional areas, depth, width, side slopes, and the longitudinal slope, etc. for the given boundary surface. Once these parameters have been determined, the longitudinal and cross-section of the channels may be drawn. Procedures are not presently available for selecting optimum channel parameters directly. Each site has unique features that require special considerations. Typically, the design of a channel is done by trial and error. Channel parameters are selected and an analysis is done to verify that the operational requirements are met with these parameters. A number of alternatives are considered and their costs are compared. Then the most economical alternative that gives satisfactory performance is selected. Next, the design discharge of an irrigation channel depends upon the irrigated areas of crops in different seasons and the water requirement of crops. The design of the canal is mainly governed by the quantity of silt in the water and the type of boundary surface of the channel. Depending upon these factors, the irrigation channels can be broadly classified into the following three types. First one, non-alluvial channels, second one, rigid boundary channels, and third one is alluvial channels. Next, losses of water in canals. During the passage of water from the main canal to the outlet at the head of the water course, water may be lost either by evaporation from the surface or by seepage to the peripheries of the channels. These losses are sometimes very high, of the order of 25 to 50% of the water diverted into the main canal. In determining the design channel capacity, a provision for these water losses must be made. The provision for the water lost in the watercourses and in the fields is, however, already made in the outlet discharge factor, and hence no extra provision is made on that account. Evaporation and seepage losses of channels are discussed below. First one, evaporation. The water lost by evaporation is generally very small as compared to the water lost by seepage in certain channels. Evaporation losses are generally of the order of 2 to 3% of the total losses. They depend upon all those factors on which the evaporation depends, such as temperature, wind velocity, humidity, etc. In summer season, these losses may be more but seldom exceed about 7% of the total water diverted into the main canal. Next, number 2, seepage. There may be two different conditions of seepage. The first one is percolation and second is absorption. For this lecture, we'll discuss percolation, and absorption we'll discuss in our next class. So what is percolation? In percolation, there exists a zone of continuous saturation from the canal to the water table, and a direct flow is established. Almost all the water lost from the canal joins the groundwater reservoir. The loss of water depends upon the difference of top water surface level of the channel and the level of the water table, that is H, as shown in figure 3.7. So this is your assignment for lecture number 22. The question is, discuss the factors that are considered in fixing the alignment of a main canal in a deltic region. I repeat, the question is, discuss the factors that are considered in fixing the alignment of a main canal in a deltic region. So the last date of submission is given here. Now we'll go through a video. And students, you can give your attendance in the chat box right now. Also, at the same time, you can watch the video. That's all for this lecture. Thank you.
Well, Colliamble Irrigation is Australia's most modern irrigation company, unquestionably. It's also one of the most modern open channel operations in the world. The big crops are cotton, rice, wheat, barley, and there's a variety of vegetables and fruits grown in the area as well. CRCL's board took the decision to modernise in 2002, and that was largely out of a desire to provide improved levels of service to our customers, to our members, and also to make serious water savings, because the board at that time could see the writing on the wall. Water was becoming increasingly precious, and every drop had to count. In all, we've got just under 1,200 flume gates, some of them are on-farm outlets, of course, and the others are multi-gate regulating structures. The essence of this highly sophisticated open channel system is total channel control technology. What that means is that right down to farm level, all the flows are controlled via a series of automated gates that are linked by a broadband communication system. It means that you can get precision control of flows throughout the irrigation system, and that all those flows are completely automated.
If a farmer wants to order water, they either do it over the web or over the phone. They can put their order in. The system automatically checks whether they've got enough water in their account. If they have, it starts the outlet at the time and at the flow rate they want, and all that process doesn't touch a human hand. We're not involved in that at all. It's all done automatically. So the 2 hours still blows people away. The fact that we can a farmer can order water with 2 hours' notice, and if it's an emergency, even quicker than that. For a lot of people that are on 7-day ordering or fortnight ordering or even 48 hours, it just makes such a difference to the farmer's operation.
Prior to Rubicon technology coming along, typically a farmer could get 8 to 9 megalitres per day onto their property. We've got farmers now who are taking 100 megalitres per day onto their property, and we're about to connect somebody who will take 300 megalitres a day. That fast water on and off a crop is the most efficient way. So there's water savings if you can water more quickly.
We basically think we've got the system to a point where our losses are pretty much fixed. So it doesn't matter whether we're delivering 100,000 megs a year or 400,000. We think our losses are pretty much consistent. And so we're down to basically some seepage, evaporation, obviously, and that's about it.
We've seen the level of water losses drop from, on average, about 100,000 megalitres per year, now down into the area of about 30,000 megalitres per year. In fact, last year we had our lowest ever losses of about 26,000 megalitres. Now that saving of 65 to 70,000 megalitres year in and year out is an enormous saving, and that saved water goes back to our members as additional water.
In the years where we had, 06, 07, we were given 10% from the state off the river, and we were able to give another 17% internally to our customers. It was the difference between some of them going broke or staying in business. That was probably the time we went from some of the farmers being against the automation stuff to wholeheartedly embracing it when they saw the benefits like that coming back to them.
So you can appreciate just how valuable those water savings are. They've allowed us to provide an improved level of service, and they've meant that our farmers, in fact, get access to more water, not just the water that's been allocated through the water sharing plan in Australia, but also those savings made by the company itself. So that's cemented the relationship between the customers and the company. That's given the business itself greater certainty of revenue. It's also that greater certainty of revenue has meant that we've been able to stabilise our pricing. Our customers are now paying less in real terms than what they were in 2008.
The other great thing that we've found out of the system is just the level of data you have. Everything in the system is logged. Your flow rates, your water levels, the battery voltage, the solar panel voltage, the amps drawn, everything. We're currently trying to fix up our system to improve the capacity of some sections, and the data we get out of the system is just gold, because we can go and look at particular regs and say, okay, what flow can we get through this? Not what the theoretical is or what the design might be, but what have we physically got through there when we've pushed it really hard. We've got all that data, we can go back and look at it.
From day to day, we do monitoring of the system, repairs on flume gates, and just day-to-day housekeeping. The gates are easy to maintain once you're up to speed with the technology, and they're built well and they're reliable.
We're pretty much a business hours staff now. We do have people that watch the system after hours, and I'm part of the group that does that from time to time. But it's you do it from home, you log on for 5 minutes every hour. If something goes wrong, you can log on and fix it. But I went camping over Easter and watched a particular channel. I could do it as long as I had comms back here over the internet. I could do it. And there's a lot of things you can fix in the system remotely.
What's really interesting is that the National Water Commission has, over recent years in Australia, benchmarked irrigation delivery systems, and we've consistently come out as the most efficient open channel operation in Australia. If you are delivering water more efficiently, you're in a position as a company to decide whether or not you can make water available to address local environmental needs. Less wastage is good for farmers, but it's also good for the environment.
So I guess any system that is manual and is looking at automation, I'd be recommending the Rubicon system. I've always said, there's a lot of others dabbling in this space, but I think Rubicon's 10 to 15 years ahead of anyone as far as the fully integrated system with both the hardware, the software, the algorithms that run all the channels and everything like that. So, yeah, I'd highly recommend it.